Hello and welcome again to my Physics Online video lecture series. Today's video, I want to be talking a bit about longitudinal stress and strain. That goes with the idea of tensile elasticity and of Young's modulus. Now, as we do in all of our other videos, we might begin this video by reviewing a little bit of where we have been. So let's recall what the main salient points have been so far in this series of lectures about stress and strain. The main thing is that we want to work in the linear regime of elasticity, and that in this linear regime of elasticity, we should be able to say something like the strain is given by some modulus of elasticity, which is constant, times some stress. Stress, which is our sigma, is defined using sigma is some amount of force per unit area. The strain, which we use an epsilon for, is defined variously. But we might say that it represents sort of like deformation per uniform per unit length. So you could call this like normalized deformation in some sense. All right, so that is enough for us to use for our recall. In today's video, what we're looking at is the case where you have an object which has some sort of a length and some sort of a cross-section area that may be given in this way. All right, so this right here would represent, let's say, our unchanged length, and our cross-section area then would be essentially the cross-section area in this direction. And what happens is that we apply some force, and the force could be to stretch or to compress the object, but we have some amount of force being applied on both ends. For example, this could be a rod that is being held in a vise on one end and maybe being held in a vise on the other end, and one of the two vices is being pulled away from the other vise. And so what happens to this rod under these circumstances is that instead of going just to some initial length, it actually kind of stretches out a little bit. So this strain right here comes from a delta L. And so my epsilon in this case would look like delta L per unit L naught. My stress is however much force this is divided by whatever the cross-section area of the sky is. And we're assuming a uniform rod here, as opposed to, say, a conical shaped rod or something like that. Okay, so basically, this modulus of elasticity, in this case, is called Young's modulus. And the Young's modulus is generally specified for different materials. So essentially, it's something that you can look up in a table given for different materials. And so essentially, this is the kind of thing that engineers especially excel at. They're great at you give them a problem, there's some standard value, and they go look it up in the table, and they say, okay, you've made this out of, let's say, iron, and therefore the Young's modulus of elasticity for iron with these dopants would be this number, and maybe that changes with temperature and so on and so forth. My goodness. For example, we could go to the engineering toolbox, which is kind of one of my go-to sites for looking up stuff like this. And they have on their website this nice table, which has, among other things, the Young's modulus of elasticity. These are specified in gigapascals. That means basically that they're specified in times 10 to the 9, pascals or 10 to the 9 newtons per meter squared. And you can just kind of scroll through and look up whatever material you're trying to use. So like here's aluminum, 69 gigapascals. Bismuth, compact bone, spongy bone, brass, bronze, cadmium, etc. And you just would go through and try to look up for whatever material it is that you're trying to determine the Young's modulus of elasticity for. You've got diamond, Douglas fir wood, glass, whatever, platinum. And so you just look up the value, and this represents your Young's modulus of elasticity. Usually when we're doing this longitudinal stress and strain, we replace the M modulus of elasticity with a Y for Young's modulus. So typically we represent it with Y. All right. So as I said, we typically represent Young's modulus of elasticity with a Y instead of an M sub E. The units for that, gigapascals, that means times 10 to the 9 newtons per meter squared. And this is kind of the key concept here. A larger modulus of elasticity typically means an object which is less stretchy and therefore more stiff. So if I have a very large modulus of elasticity, it's harder to make the object stretch when you pull on it. All right, so we looked up some values on this engineering toolbox. So let's maybe make use of one of them and do a simple example. Before I go into the example, it's worth noting that there's such a thing as like an ultimate tensile strength and a yield strength that we aren't really interested in talking about today. But they, in some sense, put some limits to some of this stuff. So you can exceed some value of stress and of strain and have the object that you're applying this to just simply fail, like it breaks. And so I'm not trying to figure out, is the object that I'm doing this with going to break or not break? I'm just kind of interested in assuming that we can apply this much force and this much modulus of elasticity, what will happen? So let's use structural steel, this guy right here, for our example. And so this is 200 gigapascals of tensile modulus. So we get this structural steel bar with a known radius and known non-stressed length. We place it in a hydraulic press, and this happens to apply a compressive longitudinal force of 25 kilonewtons to the bar. So we want to know how long the bar will be with this stress kind of applied to it. So basically applying force like this of 25 kilonewtons. All right, so here's your bar. There's 25 kilonewtons being applied to it. The radius was given as 5 centimeters. So we expect to have stress is equal to Y, Young's modulus times strain, and that means that the strain should look like the stress divided by Young's modulus. Okay, the stress in turn is the force per unit area, so that's force over area divided by Young's modulus. We can combine all these terms, knowing that the area is pi r squared. This becomes force divided by pi r squared y. Therefore, your strain is going to be 25 times 10 to the 3 newtons divided by 200, so that's 2.0 times 10 to the 11 pascals times pi times the radius 0.05 meters quantity squared. Strain is thus 1.59 times 10 to the negative 6. The strain in turn is basically how much we've stretched divided by the unstretched length. So that is your strain. That means that the amount of compression would be L naught times epsilon So if you multiply this number by 2, you get basically about 3.18 times 10 to the negative 6 meters, because this again is 2 meters. That means that the actual length will now be 2 meters minus this number, which with any reasonable significant figures is still 2 meters. We don't have very much compression here. On the other hand, a hydraulic press can actually apply a lot more force than this. So maybe the hydraulic press, instead of going to 25 kilonewtons, goes to 0.25 giganewtons or 250 meganewtons. Well, that moves this decimal place quite a few spaces over here, and so soon you end up with like a 3 centimeter compression, which is actually noticeable. So that's all that I wanted to talk about in today's video. Hopefully you've learned something from this video. Thanks for watching.